Okay, so we will be continuing our discussion on the linear discrimination based classification. And in the last class, we have discussed about the problem formulation and then the, you know, the cases for the linear classes, how the uh, linear discriminant function can uh, classify the samples into two classes. We also discussed about support vector machine, and which optimizes the margin of separation between two classes, particularly when they are separable, linearly separable. Uh, for that case, we have discussed. Today, we will be continuing that discussion, and we will consider the case when these classes, they are the samples of the classes, the way it has been given, they are not linearly separable. Now, you can see here that uh, they are not linearly separable here. It means that uh, if you consider the convex hull, because in the last class I mentioned this particular question that no, what is the criteria by which you can check whether they are linearly separable or not. So the property, very easily you can verify that if you can form convex hull of these classes, then the convex hull should be non-overlapping. So if they overlap, if they intersect, then there does not exist any hyperplane which will clearly separate them into two halves. So that is the issue. So in this example, we have shown that the triangles, they show samples of a particular class, and the rectangles, they are showing the samples of the other class. And if I take the convex hull diagram, I mean, it's in two-dimensional space, you can see that they are overlapping. So which means no, you cannot get a straight line here in the case of two dimension, which will clearly separate them into two hubs, where the positive hub will contain one of the classes and the negative hub will contain the samples of the other classes. So under this scenario, how this problem can be formulated, how we can set another, modify the uh, objective functions of the optimization problem, that we would like to discuss here. So here, intentionally, I have shown a sample which appears to be intruded into the region of the other class by a different color, like I have shown it by a red color, as you can see. And in this case, what we'll do, we'll be introducing some additional variables, which are for each sample, which are called slack variable. So slack variable actually provides a tolerance from the margin that we are allowing when we are defining an hyperplane. We would consider those hyperplane which also, no, these hyperplane are also, they allow also certain tolerances of the samples which may go into the other half. So slack variables are the measure of that tolerances, which means the distance of that sample from the hyperplane. So here in this diagram, we have tried to explain this particular thing. As you have seen in the normal linearly separable cases, we consider a hyperplane like no in a directions. So as you can see that this is the normal to the hyperplane, and then there are two uh, parallel hyperplanes of the same directions, and where no, they are just touching the some of the samples which lies on those hyperplanes. They are the support vectors, and they define those planes. We have seen in the optimization problem how we can compute those hyperplanes from them only as a linear combination of those samples only. So, but the idea here is that this sample, which should have been in the positive half of this one, this hyperplane, it goes to the other half. And not only that, it actually, since you know that in actual test cases, test hyperplane would be in between these two. That means which passes through 0. So WTX plus W not equals 0. So that is the test hyperplane. So it even it no it goes beyond that. So it there is certain tolerance already, but it may also lie within that tolerance, or even it may breach that barrier, and actually it gets misclassified. So in that case, the this we are allowing. So we are allowing certain misclassifications during the choice of hyperplane. So the deviations from the hyperplane, or the distance from the hyperplane, is measured in terms of this standard definition, geometric definition of the distance. It is the no, it is a distance length of the perpendicular drop from that sample to the hyperplane. So let us consider this distance as S. So for every sample, there is some distance. As you can see that only thing is that only we are considering the samples which are deviated, which are going into the other side of the hyperplane. Then only this distance is measured. Otherwise, this distance would be taken as 0. So this we call as a slack variable. So S is representing slack variable. So these variables are also introduced. So when we are optimizing the objective function, we have the parameters. So the parameters are used for optimizing the objective function. As you can see that primarily the objective was to minimize this this separation between these two hyperplanes, to the two margin planes, of course, of the same directions. So which means the distance is this. Distance of separation is this 2 by of the norm of W, and uh, so effectively we are minimizing W. So this is what you will be doing, and we'll be actually minimizing the square of the norm, half of square of the norm, plus these slack variables will put some constraint on the formation. So there are certain constraints. So we'll see how slack variables will be defining those constraints. So this is the defined problem or modified problem with using the slack variable. You can say earlier we have considered the constraints only. This is what we have considered for every training sample. You know that RT is a class level, which is either plus or minus 1 for the TH sample. XT is the corresponding featured sample, feature vector of the sample. And this is the parameter W and W naught. And we want that the whole thing should be always greater than equals plus 1. Now, due to the tolerance, introduction of this tolerance, now it should be 1 minus ST. And ST has to be always, greater than 0. ST has to be always greater than 0, and the whole value should be greater than 0. So the ST should lie, ST should be positive. So for the samples which are lying in the right half of the of this, which are satisfying directly this plus 1, so for them the ST would be 0. So this is this slack variables are the introductions, as I mentioned, and so there are ranges. So if ST is between 0 to 1, we know that XT is correctly classified because of this, because as I was mentioning, there is already a tolerance. See, this is your test hyperplane, and these are the margin hyperplane which you are considering during putting constraints. This tolerance is between 0 to 1, still XT is correctly classified, right? Though no, it is not satisfying this hard constraint of the linear SVM case. With the slack variable, it is satisfied, but still it is correctly classified. Once ST is greater than 1, then actually this sample will be intruding. I'm talking about with respect to this hyperplane. So this sample will be intruding into the region of the other class. So then XT will be misclassified. So these are the two interpretations of ST. So with this, we can say that because for every training sample, you will be computing also the slack variables during optimization. So you'll be computing the parameters and also slack variables. So if a number, so the number of samples for which ST is greater than 1, that also give you the number of misclassified points. So that is what. And if I consider it is greater than 0, it is basically number of non-separable points. and then no, we may consider soft error is sum of. So this is the error we are be introducing. So we are trying to minimize this sum of this values of slack variables, sum of st, because it's a minimization problem. So we can consider that our objective functions will be modified in this way. So we are minimizing not only the square of the norm of the weight vector w, but also the sum of those slack variables, and it's a linear combination. So C is a constant. C is some constant. It's also a hyperparameter. C is also an hyperparameter. So depending upon the value of C, your result will vary. Okay, just so that's what C is the penalty factor here. Now, if I put it into an unconstrained form using the Lagrange multipliers, because you are using a new set of variables, we will be having a new set of Lagrange multipliers. As you can see that we have also the mu t, right? This other than alpha t, we have also mu t because of this equation, this part, right? Because of the we want to minimize it, so uh, we are putting this constraint here. With, st has to be sum of st, and this has to be also greater than 0. So alpha t into this, and yes. So this is a new Lagrange multiplier constraint, right? To guarantee that st greater than 0. That's what I was telling you. That the other constraint which I have not mentioned here, subject to, like I should have mentioned also here, that for all t and also st, right? St greater than 0, greater than equals 0. So for that, you have to put uh, this Lagrange parameter. So if I convert into a dual problem as before, we can consider the corresponding optimization problem with respect to the Lagrange multipliers, and we can see that these are the new set of equations that you are getting. So what you will get this. This is constraint that you will find that I mean the same dual problem you will see, but now your modifications here. In this case, you have this. Right? When you put these things with respect to st, if you uh, if you consider this, multiply this, then you get these equations. Okay? C and alpha t, that is coming. I think mu t is taken as 1 in this case, because that is what I find, right? So you have this equation. So mu t is a parameter here, which is taken as 1. Yes. Right. So the new constraint is that earlier in the earlier problem, alpha t was supposed to be just positive or equal to 0, but now it has to be limited by c because of this new constraint, because of this constraint. That is the interpretation of c, hyperparameter c. So alpha t will vary between 0 to c. Right. So this is the dual problem, and you can solve as before by using the quadratic optimization, and we can get the corresponding support vectors which will be lying on that particular border. That means the values of alpha t will give you the solutions itself. The values of alpha t itself will give you this as before, the same, weight vector for the hyperplane. That means normal to the hyperplane. And for the bias, once again, we'll follow the same methodology. That means we'll find out the support vectors. We'll find out the support vectors. And then for those support vectors for which the alpha t is greater than 0, we'll compute the bias and we'll take the average. So this is the approach when you are using slack variables and which can deal with the non-separable cases. Now there is another way, I think that is a bit better way where in fact we can consider it's a kind of non-linear SVM, but it could be a linear SVM if we project those samples in higher dimension. That means even if the linearly non-separable cases, if I add a dimension, they become separable. So you consider this particular example. Say the same example. Now, if I add another dimension, for example, and in that dimension, these two corresponding two training samples may be separated out. So with some transformations of the feature vector, we can perform this particular, and we can make them linearly separable. So with appropriate transformation of the coordinates and transforming it into a higher dimensional space, that means from lower dimensional space to higher dimensional space, that is a transformation. Then you can make them linearly separable, and then you can solve the problem in that dimension itself, and solve the problem for classification. So, which means that if I give you any new vector, this same transformation has to be performed, and the corresponding hyperplane in that higher dimensional space, which is used for discriminating the two classes, that hyperplane should be used. So that is the idea here. But we'll see that there are certain tricks by which these computations can be simplified. So, if I formulate that problem with these projections, of a feature vector to higher dimensional spaces, let us consider that we are projecting it to a k-dimensional space. That means given a feature vector, maybe feature vector dimension of the feature vector expected to be smaller than k, and there are j such basis functions from which you can get k-dimensional space, and then you are defining the linear discriminant functions there. So there you can also consider that your constant term is also providing you another dimension. So that is also included into the corresponding the transformation, that basis function itself. So that's why we are representing it by the linear form. That means we can directly write. So one of the basis function can be a constant here, which means, right? So so this is the discriminant functions that you can see here. But the problem is that even after that, it is not a guarantee. Like heuristically or intuitively, it should give you a better power of separability. But no, it is not. There is no guarantee that it would be separate. So still, you can use the same slack variable concepts. That means a more general case. So you solve it into under the same setup, because since it is not guaranteed, it is better to use the general formulation of the problem when the linear non-separability is also considered. Only thing is that instead of the feature vector x, now we'll be working with the transformed feature vector in high dimensional space, like phi x. Okay, so that is how the problem is formulated here. So you'll see it's almost similar problem formulation here, and the results are also similar, because instead of x we have phi x. So it looks like this, that that we are taking the dot product of two samples earlier, but instead of that we are only taking the dot products of the high dimensional, or the transform feature vectors. Now here the interesting fact is that if I give you this dot product value of all possible combinations of training vectors, training samples, or even you consider given any 2 points in the feature space, if I give you their dot product value only, the actual values of the feature sample is not required. Only the identity of the points. So points can be indexed in various ways. So that is only required. But for some, say from some other way, you might be able to compute this particular quantity, and in some other form, you might be able to compute this quantity. Like it's a kind of dot product means it's a kind of similarity measure between these two. So you can use that, and we call this kind of function as kernel functions. So you can use kernel function instead of directly using this, and then subject to all these particular things, you have these functions. So your discriminant function also looks like in the same form. Instead of your, you see that this is your test feature vector, and you need to know also kernel function between the training samples, any training samples which are support vectors with the test feature vectors. If you know the kernel functions itself, if the kernel function is known to you, the absolute values of the feature vectors or absolute transformation is not needed. So that is what absolute transformation is not needed. Just the kernel function is needed, and that saves the computations. So the result is so that is a interesting part of this. So sometimes these values are given empirically also, and in the form of a matrix where all possible data points, including the test data points, they are given, and their kernel values are given. There are certain properties of this kernel matrix, as you can see. They have to be symmetric, and also there are some other issues like the metric properties of distance function. Similarly, kernel function also has a property to satisfy this property of a kernel functions. So this is the property that it should be symmetric and it should be positive semi-definite. The positive semi-definite definition is this, that it has to be real symmetric function. And if I consider these computations, that means, right, basically, if I compute it's a kind of quadratic computations on that feature space, Z transpose MZ, then it has to be positive. Okay, so that's why it should be a positive. Then it is basically positive semi-definite for any non-zero Z. So that equality actually make it semi-definite. If the equality of 0 is not there, then it is definite. Right. So if it is provided, then your solution is you can use it in the computations very easily. So some of the kernel functions satisfying those properties, that symmetric and positive semi-definite kernels given data points. So this is one kernel functions, for example. You can see that it is dot product of two feature vectors plus 1 to the power raised to the power q. That's polynomial of degree q's. Then radial basis function. This is also another kernel functions which looks like a the Gaussian distributions kind of thing. Then Moholy-Neves kernel function also in this same way of Moholy-Neves distance function. Similarly, we are defining Moholy-Neves kernel function, distance function based. So distance function can be used in the kernel function in the exponential form, because as the distance increases, the value of the kernel would be decreasing. So it should be a kind of inversely proportional to the distance. In that way, I mean, as the distance increases, kernel value should be reducing. There is another kernel function. So these are some examples, typical kernel functions which can be used for solving this problem. So a typical example, it has been shown from this book itself. Just figuratively, it has been shown in a two-dimensional space. you can see that how the corresponding the decision boundaries that is defined like the hyperplane was the decision boundary for the linear SVM cases, but in this case it's since you are using nonlinearity by introducing kernel functions, so your decision boundaries are not linear, like they have different kinds of shapes. So this is one kind of shape that has been shown here, and this decision boundary is obtained by this that degree 2 polynomial, quadratic polynomial of the kernel functions. So in fact, it can be shown that this is equivalent to transformation of the feature space into the 6-dimensional space, and if I apply the linear SVM in that 6-dimensional space, you will get the equivalent result. But using kernel function, all these direct computations are not used. So simple kernel functions will be providing you this kind of classification. So in the projected space, it becomes linear, but in the original feature space, these decision boundaries are nonlinear. So that you should understand here. Right. So the other advantage of this particular approach is that you can make it further, you can further generalize it. Like the kernels need not be computed using numerical, numerical values of the feature base. Kernel values could be computed from some microphone is on. Mute your mic. Somebody's microphone. Is there anyone who can unmute? I think Mannan Baidi. Yeah. Right. So as I was mentioning that now for computing the kernel values, kernel function values, it need not be computed using only numerical values. So the notionally this kind of measure of similarity or even the distance as you consider, that can be obtained from different other procedures also, whether numerical um, computations, numerical mathematics may not be used. For example, you consider, say, number of shared words of two documents or edit distance between two strings. So these can be also used for defining a kernel matrix. Right? So or any empirical definition itself, as I was mentioning. So you can use it and then use this kind of this same approach or for solving them using SVM. So just to summarize whatever we discussed about this support vector machine, you can see that support vector machine provides a maximum margin based linear discrimination for two linearly separable classes, and the approach can be generalized for even for non-separable classes by using slack variables, or even you can use basis functions to map non-separable class to make it separable in a high dimensional space. Then if you use kernel functions, this computation becomes simple. So do you have any questions till this? We'll still continue our discussion on this linear discriminant based classification. We have earlier discussed about parametric classifier using Bayesian theorem. You can see that we considered this by modeling the probability distributions even in the multidimensional spaces, that Gaussian distribution. There, the likelihoods, particularly because the Gaussian distribution, you have that exponentiation term. If I take log likelihood, you get those terms as a polynomial term, and which is also a kind of discriminant functions in the polynomial degree. And in certain cases, in some special cases, they become linear. Those special cases are that if you have the same covariance matrix for every class in that Gaussian likelihood distributions, then you can show that those classifiers are same as the linear discriminant classifiers, or the functions are linear discriminant functions, linear functions. So as we discussed. So this we have discussed in the previous lectures. So we'll just revisit them, and because we are discussing about this linear discriminant cases, and we'll see that uh, there is a special kind of classifier using this concept. So same Bayesian um, Bayesian classification scheme can be also expressed. That approach, Bayesian approach, can be also expressed in the form of linear function, linear discriminant function. Because we have seen from the other angle, that means assuming the Bayesian or applying Bayesian decision theory, we obtain those linear discriminant classes. But now you consider the other way. Suppose we are going to design a linear discriminant function, but um, our objective would be, while designing these functions, we would like to apply the Bayesian decision process. So we'll see that. I mean, how to do that, and that is basically the method approach is known as logistic regression method, uh, which can be used for classification also. So this is the result. That means discriminant functions, when we have more number of classes, like more than one classes, in fact more than two classes also. So there, for every class, you have in its class likelihood, you have the set of parameters. Uh, as you can see that the parameters would be given in this form, that the likelihood distributions, you have mean vector, you have the covariance matrix. So the weight vectors, that means the normal to the hyperplane, is given by this expression. That means inverse of covariance matrix and multiplied by the corresponding mean vector of this likelihood class. And whereas the corresponding bias term is given by this value, and this is a scalar value. If you can see that this is a scalar value, this is computed again from the covariance matrix and the corresponding mean vector, plus this value, it is coming from the prior distributions, because in the Bayesian inference mechanism, we are maximizing the posterior probability. That means we are maximizing the probability of a class given the data, given the sample. That is the posterior probability. So, use of prior is there in this case, because prior multiplied by likelihood will give you, divided by the marginal probability, will give you that posterior probability. And since marginal probability is the same for every classes, we can ignore that that element, and that's how the discriminant functions become simple linear discriminant functions. Now let us rather consider the problem is formulated in this way, that directly we will be estimating these posterior probabilities. So we'll see that how we can relate these discriminant functions with these posterior probabilities. So that is the interesting part. Once we understand that, then the problem formulation of logistic regression will be clear to you. So here, let us consider that we have two quantities, because we are assuming two classes. So posterior for class 1 and posterior for class 2. So given a sample, so posterior for class 1, say you consider the value is y. So naturally, posterior for class 2 would be 1 minus y, because there are only two possibilities. X could be either assigned to C1 or X could be either assigned to C2. So with probability y, it could be assigned to C1 with this probability. And with probability 1 minus y, it could be assigned to C2. And naturally, if y is greater than 1 minus y, then according to the Bayesian inference rule, we will be assigning x to C1. So we will say that we can choose C1 if y is greater than 0.5. It is fair enough, because if y is greater than 0.5, which means 1 minus y must be less than y, right? Or even we can write y by 1 minus y is greater than 1, right? All are equivalent. Or we can write log of y by 1 minus y greater than 0, because no, if I apply log operations, it should be greater than 0. So you see that in various ways this criteria could be put. Uh, all are equivalent. Now, why it is represented in different forms, that we'll see because of the analysis from the point of view of analysis. Sometimes some representations are convenient to handle. Particularly the logarithm operation, as you can see, when you take Gaussian distributions, because of the exponentiation term, if I take log, now those term becomes polynomials. So instead of exponentiation, we handle with polynomials, and sometimes those polynomials also can be reduced to a linear polynomial. So that is the advantage of having logarithmic transformation. So we express the criteria also in the log space. Now there is a term uh, which is a function of y, and this is a function called logit function. So this logit is uh, very interesting term, a very interesting function. So this is the definition. So if I say logit y, it means log of y by 1 minus y, right? And what is y in this case? Y is the posterior of class 1. So in our reference, y is the posterior of class 1. So if I say logit of posterior of class 1, that value, if suppose this value logit of y is z, then inverse of that function will directly give you the posterior probability, right? So that is very interesting, right? Inverse of that function will directly give, because y is logit inverse. So inverse of that function will give you that. So once again, let me uh, put this consider condition. So you see that now I will be writing logit of probability of C1 by X. So this is the trick. So here the logit function itself is considered, that's a linear function. That is a linear discriminant function, or linear function W transpose X plus W naught. Okay, so where W is epsilon inverse, sigma minus mu1 minus mu2, because you are handling two classes, as you can see that you do not require two discriminant functions. So one function is sufficient, and we are considering that itself is like this, and W naught is this. Okay, so the inverse of logit is the logistic function, also called sigmoid function. So how do you express this inverse? If you do some algebraic manipulations, you can show that this inverse can be written in this form. So it is 1 by 1 plus exponentiation of that term. So which is called sigmoid function, right? 1 by 1 plus e to the power minus z, that is a sigmoid function. Sigmoid function of. So inverse of the logit function is the sigmoid function. So this is also another function. We'll be also encountering this function during the discussion of neural network. We'll see that. Right. So this is how we are considering these computations when we are using the parametric 2+ classifications. Estimate these parameters, then compute coefficients of gx, that means w and w naught. During testing, calculate gx, then assign c1 if gx is greater than 0, else c2. So this is the standard parametric classification. So far, nothing is with respect to the logistic regression. It is, I mean, it is. We have already discussed this. So this is a method. Or in the logistic framework, that means when we are considering the logit function, we using that w and w naught, we can calculate also the posterior. Earlier, we are not calculating posterior. So in this case, you can see that we are simply using this rule for class assignment. But here, we can calculate the probability of C1 given X from this value. So it is giving you the posterior probability. I should say posterior probability with proportional term. I mean, it is giving posterior probability. Of course, if you can normalize y between 0 to 1, then it becomes the same. So we are considering that only here. So that normalization is taken care of by this W and W. So this one is assigned C1 if y is greater than 0.5, else C2 is 0. Okay. We consider this that ratio of class densities you are modeling. So assume log likelihood ratio is linear. So we consider that the ratio is this, uh, but that is true for normal density functions. As I mentioned, this log likelihood ratio uh, can be written in this form, and then logit of posterior can be written. Actually, this is not the log likelihood. This is log of the ratio of the posteriors. You know, the ratio of the posteriors has a relationship. We can write it in the, okay, because the logarithm operations, it can be shown it is a ratio of the log likelihood. It is basically I mean, it is a log likelihood ratio plus, log of the ratio of the priors. So this is how it is related. So W transpose X plus W naught can be directly this term. So this term comes from here. So that's why W transpose X. And since this is also a scalar value, so you can simply add them. And let me write W naught prime and this as W naught. So this is the relationship. So how the relationships, what is the relationships between the discriminant functions in the logistic framework is that if I use the discriminant functions, you can design a discriminant function in such a way that its inverse, logit inverse will give you the directly the posterior probabilities. So we'll be considering a problem formulations where we'll be directly computing that, and then it becomes a logistic regression. So we'll see that what is the advantage and how it is used for the computations. So this we have discussed earlier. So what is the learning problem here? What is the learning problem here? So we are learning these weights under the Bayesian framework. Again, implicitly, the Bayesian framework is working behind. So let us consider once again, let us see these computations, and we can understand better uh, this particular process. So once again, the data is given in the same form. That means you have the class levels and you have the feature vectors for training samples. And in this case, labels are 1 or 0. And we consider that the say y, similarly, y denotes the probability of class assignment to the class 1, probability of class 1 given the feature vector x. So naturally, uh, see if suppose y is the parameter of a Bernoulli process, so a sample can belong to class 1 with this probability y, and similarly it can belong to class the other class with 1 minus y, but it is given the data itself. So as I was mentioning, it is directly modeling it. So if I consider the uh, now you see that every sample this probability will be different. So y is not a constant here. Y is basically I could have written uh, here, which is should be written. It is xt. This is also, that means this is for tth sample, and this is a Bernoulli process for tth sample. So we can consider that given the data, so likelihood of the parameters that can be expressed in this form, because for every sample we can use, for every sample you see that either yt or 1 minus yt, either one of these term remains, and it's the product of all these terms given the n x consists of n samples. So that's why it's a product of all such Bernoulli, all such probabilities of samples given the levels. You have to consider that. So that would give you the corresponding likelihood. So our objective would be to estimate those y. Rather, I should say our objective would be to estimate those w and w naught, right, which will maximize this likelihood. Which will maximize this likelihood. Because if you compute W and W naught, that itself will give you YT. Given W and W naught, what is the relationships? Because the linear function would be W, say given xt, linear function would be W xt plus W naught, right? That would give me a value. Let us consider that value is zt. So, so yt is the logit inverse of zt or sigmoid of zt. That means 1 by 1 plus e to the power minus zt. That is what is your yt. Similarly, you can compute. I mean, that is how you compute. And uh, your objective would be to maximize this likelihood, so that no, that means to determine that W and W naught which will maximize this likelihood. So it's an iterative process. You can see that it's not really the linear regression problem. It is objective is different here. So I can either maximize it, or I can minimize the negative of, I mean, if you take the logarithm, because it's product, that's a common trick for any maximization or minimization problem of a product. We do it in the log space, and then the product becomes a summation, and then, but still the problem remains the same. That means maximization remains the maximization problem. Since you are taking the negative, it is now the minimization problem. So E is E is your objective function. You have to minimize the objective function, which is the minus of this. So if I take the minus of this, so just to make it clear, this diagram. Okay. So you get this expression, right? So you get this expression. So your objective is now, finally, this is the objective function. So choose that W naught, which will minimize this E. Now, Y is computed from W and W naught. So iteratively you can do, and you can apply the gradient descent method. So you can do that. So because it's sigmoid function, you can see that how the sigmoid, the derivative of the sigmoid is very interesting. It can be computed from the functional value itself. You can prove it. So if I consider say the derivative of that function at that point, the function value directly can be used for computing derivative. So that is what we are using here, and it can be simplified. These expressions are simplified in this form. So many a time this kind of learning, Avian learning framework is there. You can see that interpretation is very simple, that for every feature component, its corresponding Wj is the corresponding parameter with respect to the jth feature component, jth dimensional component. This is true level, and yt is your posterior that you have computed. Yt is not a level. Yt is your posterior that you have computed in this. So that difference and the negative of that is the learning. That is the weight update rule. And W naught can be obtained in this fashion. So you just apply it iteratively. You do it iteratively till it converges. And that is how you get all the parameters. So this is what is the final algorithm. You compute W and W naught, and you can extend it to multi-class because what you are using using the sigmoid functions. There you can use softmax functions to compute those corresponding Bernoulli's parameters, corresponding probabilities, posterior probabilities, and this is your likelihood function. So you can just modify your problem in the same spirit. So with this, I think we have covered mostly whatever we wanted to cover under this topic. As you can see that first we have considered the discriminant functions, and which could be explained also in the Bayesian inference. And at the end also we have seen how these are very much related. So in the previous case, from the Bayesian inference, from the Bayesian theorem, and using the probabilistic modeling, Gaussian probabilistic modeling, distribution, Gaussian modeling of probability distributions, we have derived the linear discriminant functions. But the other way, that means from the linear discriminant functions directly you can compute the posterior probabilities, and you can maximize the likelihood of the class levels, of the samples, as you can see, under the same framework. That is also very interesting. So we have also given geometric interpretations of hyperplanes and the separation of space. Then the formulated the objective functions for the support vector machines, and also the objective functions for obtaining a solution in the space for the linear discriminant functions. Of course, that solution may not be unique. So you can use this gradient descent method. You can use stochastic gradient descent, which is single sample relaxation technique. Then linear SVM we have discussed, and finally we discussed about this logistic discrimination, or which regresses posterior directly from the level data that we have seen. So with this, let me stop here today, and let me know if you have any query. In the meantime, let me download your attendance. So if you have any query.
Good morning, sir.
Yeah, tell me.
Sir, I noticed that 2 days back the answer key for question 10 in quiz 2 was revised, and the marks were re-evaluated. I had a query regarding that, sir.
Yeah, please tell me.
So actually, it was a multiple select question, and initially the correct answers were A and B, and then later the correct answers were made to be A, B, and C.
Yeah.
So shall I?
Let me explain. Actually, the question was on a priori of the
yes,
the a priori algorithm, no?
Yes.
What is that algorithm? A priori, right? So there, the question was the association. When you are finding associations, whether you are finding associations on the attributes or on the values of the attributes, right? There is one option was there like this. There are two options, but see, actually, there are certain situations when even the attributes are also associated. So somebody has pointed out, and we agreed. So that's why both the options are correct. Now, for a single question, because now if the attribute is multi-nary values, there are multiple values, then the association among values are to be considered. But if the attribute is a binary attribute, then attributes can be associated. Okay. So that's why.
So then both of them should be marked, or shouldn't it be like either AB or AC?
No, both of them. See, when it is correct, both of them are correct.
Okay, sir.
So total marks is 6. See, in all multiple choice, total marks I keep it 6, so that sum of your positive and negative marks becomes 0, right? So this is the kind of constraint we have, and since it is total marks 6, now this 3 is divided into 2.
Yes, sir. I saw that. Okay.
Okay. So again, no, tomorrow we'll meet. Thank you very much.